Okay, so we've talked about fractions. We have some part of a specified whole, and we have some number of those. So we have groups of a size of a whole. We've talked about terminating decimals, which are fractions whose parts are tenths, hundredths, thousands, hundred thousands, and so on, of our base 10 unit 1, right? We have tenths, hundredths, and thousands. And so terminating decimals were the ones whose denominator, those fractions whose denominators were powers of 2's and 5's exclusively. But what about if we loosen that restriction, right? Like, if there's a message to take from this entire week and the week before, is in mathematics, we get to new ideas by relaxing some of the restrictions that we've imposed. And so what happens now if the denominator isn't composed entirely of 2's and 5's? We get the repeating decimals. Okay, so, and I've already kind of said these things, but again, let's revisit our definition for terminating. It terminates if B contains no primes other than 2 or 5. So what about those where B, the factors of B are not 2's and 5's? So for example, converting 2/11ths into a decimal using the long division process, because remember I said if it's not just 2's and 5's, we don't want to use that extended form approach, because there's no way we can multiply by 1 to get to a decimal form. And so here we use long division. So we actually get 0.18. So if you do that work, it doesn't fit into 20, or it fits once into 20, and then 8 times into 90, we're back at 2, and so we'll repeat, and we get 0.18, 18, 18, 18, and so on and so on. And because we don't want to write it, but we do want to make a note that it repeats forever, we'll use this notation, 0.18 with a bar. And that bar means this piece repeats. And so the size of that, so in this case, the 0 doesn't repeat, it just sits up front, but the 0.18 does. So the number of numbers in the repeat is called the period. So the period of this repeating decimal is 2. So this has period 2, because 2 numbers repeat over and over and over. And so, like we saw with our terminating decimals, some decimals are easier to convert to fractions than others. So 0.55 without repeating, so that doesn't repeat. 0.55 is 55 hundredths, or 11 20ths if you want to simplify. But what about 0.5 repeated? And so 0.5 repeated is going to take a little bit more work. So I'm going to say we have a number n, and it's 0.5 repeated. So we're going to do a little bit of algebra. So suppose now we take 10 times that n. So that means essentially our decimal point is going to move over. So our n is 0.5555555, and I'm not going to write anymore. And so that means 10n is 5.5, and I'll just put a bar there. How's that? 5, 5, and I'll just put a bar there. Because we move our decimal place once, because multiplying by 10 in base 10 means all of our groups get rebundled and shifted 1 to the larger place. So here we have 10n, and we have n. So let's subtract. 10n is this, 5.55 repeated, minus n, which is 0.55 repeated. So 10n minus 1n is just 9n's. And 5.55 repeated minus 0.55 repeated means that just all of this goes away, and we're left with 5. And that means my n is 5/9. But remember, n was 0.5 repeated. So 5/9 is 0.5 repeated. And so if I whip out my handy dandy calculator, 5 divided by 9, we get 0.555555, and then my calculator ends with a 6 because it has to round. And so it's important that we remember a calculator has some limits. It can't show us an unlimited number of places. So even though this technically never terminates, and it looks like it's 0.55555556, when we show our algebra here, what we end up seeing is that we get 5/9 is 0.5 repeated. And so here's your nice, neat typed up work. And so let's think about this a little bit more. So what is the fraction that corresponds to 0.9 repeated? So let's think back to our zoom in idea. Well, it's going to be close to 1, right? Because it's going to be between 0.9 and 1. But then zoom in 1, it's going to be between 0.98 and 1. Or actually, it's going to be between 0.99 and 1. And then it's going to be between 0.999 and 1. And so I want a clean page. So let n equal 0.9 repeated. Well, that means that 10n is 9.9 repeated. And I'm going to do subtraction again. Minus n, 0.9 repeated. So if I take 9 and if I take 0.9 repeated and subtract 0.9 repeated, those cancel. And I'm left with 9n equals 9. And so what does that mean that n equals? It means that n equals 1. But what is n? N was 0.9 repeated. And so it turns out that the number 0.9 repeated is the same number as 1. And so remember when we talked about equality of fractions, we talked about representing the same area. And then when we talked about equivalent fractions, we talked about the fact that equivalent fractions are different names for the same number, but they would all fall in the same place on the number line. Well, that means that 0.9 repeated is just another name for 1. And it's not the case that 0.9 repeated would be to the left of 1 here, or the left here, or the left here. It means that 0.9 repeated is at 1. It's at 1. It's at 1. And it doesn't matter how much you zoom in, it will coincide with 1 always, because it's another name for the number 1. And so, nice, neat typed up form shows us that 0.9 repeated and 1 are the same number. So that ends fraction and decimal concepts. And so the things I want you to take away from today, definition of fraction relies on parts and wholes and specifying some number or group of those parts. Decimals are special fractions whose unit or denominator can only contain powers of 2 and 5. And we choose those because of our base 10 decimal or numeral system. And then once we specify that they need to be powers of 10, fractions whose denominators satisfy that are terminating decimals because we can rewrite them as some fraction or sum of fractions with only powers of 10 in their denominator. However, some fractions, like a third or 5/9, because that denominator isn't only 2s and 5s, will not terminate, but they will repeat. So they give us a pattern. And because they can be written 5/9 is an integer by an integer, we can say that that is in fact a rational number. And we may or may not get to irrational numbers in a couple weeks, but know that there are some numbers like pi. Another one that's relatively commonly talked about is the square root of 2. So if I have a 1 foot by 1 foot square, since that's a right angle, we'll talk about the Pythagorean theorem in Math 205, but you can use that and you'll find that the diagonal of this triangle is the square root of 2. And there is no a and b that you can write The square root of 2 is 500 over 702. Like, there is no a and b such that the square root of 2 is a fraction. And so those numbers, like the square root of 2, like pi, like the square root of 5, the square root of any non-perfect square for that matter, any of those will neither terminate nor repeat. And those are called our irrationals, which, like I said, we may or may not spend much time with in here.